Hello again. Today we're going to cover the first part of section 13.2, which is derivatives and integrals of vector functions. And as always, given the circumstances, we can always be interrupted either by any of my two kids, and I apologize about that in advance. Okay, so the first thing that we want to define, so this is section 13.2, and the first thing that we want to define are derivatives of vector functions. Okay, so what did we say? By a space curve, so in three-dimension x, y, and z axis, I have a space curve. Let's say the space curve is called C, defined by a vector function r of t. Okay, where each point on this curve is defined by vector r evaluated at different t. Okay, so similarly, like in Cal 1, I have this point here defined by the vector r evaluated at certain point t, and then I have what happens when t moves from t to t plus h, and h, we're going to send it to 0, so h is very small, so this is r of t plus h. Okay, first of all, I just want to remind you of if I have a vector u and if I have a vector if I have a vector v, right, then the difference between these two vectors, v minus u, is going to be this vector v minus u. Okay, similarly, this is my vector r of t, and this is my vector r of t plus h. Then this vector here is the this vector here is the vector r of t plus h minus r of t, called the secant vector. Okay, so we want to define what is r of t plus h minus r of t over h, and then we keep in mind that h is small. Moreover, we're going to send h to 0, which means h is between 0 and 1. So this is also going to be a vector, because I have a difference of two vectors results in a vector, and then I divide it by a constant h, which is also going to be a vector. A vector divided by a constant, it's also a vector. So how is this vector going to look? Well, because h is small, right? If I divide by a small number, then this is just going to extend the vector. So this red vector, right, is the vector r of t plus h minus r of t over h. Okay, and now, as you might assume, what do we want to do? We want to find the limiting factor of this as h goes to 0. I want to see what is going to be the limit of r of t plus h minus r of t over h as h goes to 0. Okay? Graphically, that means that as h goes to 0, right, r of t plus h is going to go closer and closer to r, is going to go closer and closer to r. So this vector here is going to get closer and closer to this point here, resulting in the, as h goes to 0, this ratio here will result in r prime of t, and that is the derivative of the vector function. Okay, so again, r prime of t, the derivative of a vector function, is also a vector. Okay, so at this point I want to give you a theorem here. For any vector defined with components f of t g of t and h of t, okay? Or simply, if we use this notation, then r prime of t is equal to just the derivative of each component. Very, very, very simple, intuitive, let's say, concept. Okay, so this is how we're going to find the derivative. Just find the derivative of each component of the vector function. Okay, so let's prove this theorem. So I want to show, we want that r prime of t is equal to f prime of t, g prime of t, h prime of t, okay? And then we start with the definition. R prime of t is equal to the limit as delta t goes to 0. And now I change just delta t and h, just because not to mistake this h with the function, with the component h of t. That's it. Nothing serious going on here. So I have r of t plus delta t minus r of t divided by delta t. This is equal to the limit of 1 over delta t as delta t goes to 0. And here we have the two vectors, f of t plus delta t, g of t plus delta t, h of t plus delta t, minus f of t, g of t, h of t. Okay, so that's equal to the limit delta t goes to 0, okay, 1 over delta t, and now difference of two vectors is equal to a difference of each components, f of t plus delta t minus f of t, g of t plus delta t minus g of t, h of t plus delta t minus h of t. Okay, then we can multiply it by this constant y, 1 over delta t, f of t plus delta t minus f of t over delta t, and g of t plus delta t minus g of t over delta t, h of t plus delta t minus h of t over delta t, okay? And the limit of each component is just going to result in, by definition, f prime of t, g prime of t, h prime of t, right? If you take the limit of each component, that's nothing else but the definition of f prime of t, g prime of t, and h prime of t. Okay, so this theorem gives us what? It gives us fast way of evaluating derivative of a vector function, and you'll see in a second with the first example how easy it is. Example, find r prime of t, where the vector function r of t is et sine of t I plus et to the power t cosine of t times j minus e to the power 2t times k. Okay, or we can rewrite this then r prime of t, the question is how much is the derivative, and as we said with the previous theorem, that's going to be the derivative of each of the components of the vector function. So prime e to the power t times cosine of t prime and negative e to the power 2t prime, and this is a very, very simple Here I have to use in both cases the product rule, and here this is a simple chain rule, so maybe I won't have space here. So this is e to power t sine of t plus e to power t cosine of t, e to power t cosine of t minus e to power t sine of t, and the last one is negative 2 e to the power of 2t. Of course, you can rewrite this slightly in a better form by factoring e to power t in the first two components, sine of t plus cosine of t, e to power t cosine of t minus sine of t, and negative 2 e to power 2t. Okay, so again I'm going to come back to this picture here just to tell you what the derivative of the vector function, what does it give us? It gives us the direction of the tangent line to the curve at this point. Okay, so this vector, the derivative of r of t, r prime of t, is parallel to the tangent of this curve at this point. Okay, so keep that in mind in order to solve the next problem. Example, find the tangent line to the curve r of t is equal to e to power 3t e to power negative 3t 3 times square root of 2t at the point 1, 1, 0. Okay, first of all, let me remind you from the definition of the vector function, we can see that this vector function is in 3D, okay, in 3 dimensions. So in that case, we have to choose, and this is your choice, whether you're going to write the vector equation of the line, the parametric equation of the line, or the symmetric equation of the line, unless, of course, is specified. Okay, if we're talking about the vector, vector equation of the line is equal to r of t times a point on the vector plus t times v, where v is a vector parallel to the line, right? And what did we just say? That r prime is parallel to the tangent line of r of t at any point. Okay, so this vector v basically can be found by r prime of t. So let's do that first. R prime of t is equal to 3. Again, just I'm reminding you that all we have to do is find the derivative of each component, negative 3 to power negative 3, and this is just a constant because the derivative of t is 1, 3 square root of 2. The second thing is that we have to evaluate how much is this vector at the particular point. But what point are we talking about? The question says at the point 1, 1, 0. So we have to determine for what t, for what parameter t, we get this point on this curve. Okay, so just by observation, we can conclude that when t is equal to 0, right, r of 0 gives us the point 1, 1, 0. Why? Because 3 times 0 is 0, e to power 0 is 1, negative 3 to power 0 is 0, e to power 0 is 1, and 3 times square root of 2 times 0 is 0. Okay, so this is the parameter that we want. So we're going to evaluate r prime at that parameter at 0. That gives us 3, negative 3. This is a constant, so for any t it stays the same, 3 square root of 2. And finally, I have what? I have a point on the curve, and I have a vector parallel to the to the tangent line. So here what can I do? For example, I can write let's say the parametric equation. X is going to be equal to the point on the curve, that's 1 plus 3t. Y is going to be 1 minus 3t, and finally z is going to be equal to the point 0, so 0 plus 3 square root of 2t. Okay, this is the parametric equation of the tangent line to this curve right here. So at this point you can go to section 13.2 and you can do the problems 13 to 16 if you want, of course, 23 easy problems to 16, and 29 to 31.